Okay, so, you're a philosopher, right? You've probably spent a lot of time thinking about, like, the big questions, the nature of reality, uh, knowledge, all that stuff.
Yeah.
But have you ever really stopped to think about what mathematics is?
Mm.
Like, at its core?
Hmm.
That's what we're diving into today.
Deep diving.
Yeah, a deep dive into the philosophy of mathematics. And specifically, we're focusing on the really fascinating and often kind of surprising ideas of Ludwig Wittgenstein. We're going to be drawing a lot from the Stanford Encyclopedia of Philosophy for this one. It's a great resource.
Wittgenstein's views on mathematics are often kind of overlooked or misunderstood.
Right.
So what we want to do in this deep dive is unpack his ideas, you know, specifically with your philosophical mind in mind.
Mm.
We'll trace how his thinking about mathematics evolved as he wrestled with the foundations of this, seemingly very abstract discipline.
Yeah, it's like watching one of the, greatest philosophical minds trying to figure out the nature of numbers and proof and mathematical certainty. And we're not just going to skim the surface here. We're going deep, all the way from his early work in the Tractatus Logico-Philosophicus, which came out in 1922,
Oh, wow.
all the way through to his later writings in 1944.
Okay.
So we're covering a lot of ground.
A lot of ground, yeah.
Okay, so let's start unpacking his early thinking in the Tractatus.
Okay, so right off the bat, one of the things that really stands out from a philosophical perspective is the sharp distinction that Wittgenstein makes between mathematics and what he calls like genuine propositions.
Mm.
These are the kind of statements that actually tell us something about the world. So in the Tractatus, he argues that only contingent, empirical propositions actually assert facts.
Right.
And they get their truth or falsity from how well they correspond with, actual reality.
Okay, so if I'm getting this right, for the early Wittgenstein, those beautiful, elegant mathematical equations that we're so used to, they're not really working on the same level as, like, our everyday observations about the world. Like, he called them pseudo-propositions, right? Because
Yeah.
they don't have that direct factual grounding.
Right, they lack that. They're not anchored in the same way.
Yeah.
Mathematical truth, for him, it's not about pointing to some kind of external Platonic realm of mathematical objects.
Yeah.
It's, at its heart, it's syntactical.
Hmm.
The truth of a mathematical equation rests on this equivalence of meaning between the expressions on either side of the equal sign.
Oh, I see.
It's about an internal relationship within our system of symbols rather than a connection to something outside of it.
So it's not about a mathematical object, like, existing out there, but it's about how our symbols connect with each other and what they mean within that system itself.
Right.
Okay, and how do we even arrive at these true mathematical equations if that's the framework?
Well, Wittgenstein, he proposes that it's through what he calls the method of substitution.
Uh,
So we start with a few kind of foundational equations, and then we generate new ones by just replacing expressions with others that hold the same meaning.
Oh.
According to the rules that we've already established, it's kind of like a chain of equivalences.
That makes sense.
Hmm.
So proving a mathematical proposition in this view, it's not about going out and checking it against the world, right? It's about this process of, like, seeing that both sides of the equation are essentially saying the same thing. It's
Exactly.
just maybe dressed up in different symbolic clothes.
Exactly.
And I remember him drawing a really interesting parallel to logical propositions here,
He does. He does.
doesn't he?
Yeah.
Like, just as we can recognize a logical proposition as being true just by, like, understanding the logical connectives and the structure of the symbols,
Mhm.
we don't have to go out and check if it, matches up with events in the world.
Yeah.
Same way we can grasp the correctness of a mathematical proposition by looking at the expressions themselves.
Absolutely.
No need for external confirmation.
No. And it's important to keep in mind, as the Stanford Encyclopedia really emphasizes, is that this core distinction that he makes between contingent and mathematical propositions.
Yeah.
Yeah.
That's something that runs throughout his entire, intellectual development.
Oh, okay. That's a good point.
Yeah.
So that's something to keep in the back of our minds as we go along.
Yeah.
Okay. Now, he also introduces this concept of formal operations in the Tractatus, right?
He does.
And this is where it starts to get particularly interesting for me as a philosopher. It sounds like this is like getting at a deeper structural level.
It is. And while it might sound, initially kind of technical, the essence of what he's doing is trying to show the underlying structure of mathematical forms. Like, what are the generative principles at play?
Hmm.
And he introduces this concept of general forms, and he uses a very specific notation for them.
Right.
So, for example, he uses this expression AXOSPQX.
Oh, wow.
Yeah. And that's meant to represent the general term of a series, like you have A and then OSPQA and then OSPQA and so on.
Okay.
So it captures that idea of a repeating operation.
Yep. And he also gives the general form of an operation, of a proposition, even of an integer,
Wow.
using these kind of bracketed notations with variables.
Yeah.
And this operation that he uses, essentially what he's doing is he's showing the architectural blueprint, if you will, for different kinds of logical and mathematical expressions.
Okay, so these formal operations are like the fundamental building blocks, or maybe like the grammatical rules for how we construct both logical arguments and mathematical statements.
Precisely.
Mm.
And the fascinating thing from a structural perspective is that, as scholars like Frascala have pointed out, the general form of a proposition can be seen as a specific instance of the general form of an operation.
Oh.
They all share this underlying structure based on that initial idea of a series.
Okay.
Wittgenstein actually defines an operation as expressing a relationship between the structure of its outcome and its inputs.
Right.
He even notes that an operation can take its own results as a starting point for further operation,
I see.
which hints at the idea of iterative processes. And that's going to be really crucial later on when we see how mathematical structures can be built up
Right.
from simpler ones.
And so how does this all connect to arithmetic specifically? Like, Frascala's interpretation, I think, offers some real insights here for understanding numerical identities.
Right, right. So Frascala, he argues that numerical identities, things like 2 times 2 equals 4, they can actually be understood as theorems within this broader theory of logical operations.
Interesting.
His suggestion is that an arithmetic identity, like math B, may S, that holds true if and only if the corresponding equation in this operational language, something like omega's PQX equal to X, that can be proven.
Okay.
And Wittgenstein himself, in the Tractatus, sketches out how an identity like 2 times 2 equals 4 could be translated into this framework. And what this offers is a way to see arithmetic not as being about abstract numbers, but as a specific application of this more general theory of operations.
Okay, so we're starting to get a picture of mathematics for the early Wittgenstein as being very formal,
Yeah.
syntactical, and built through these fundamental operations. Now, the encyclopedia brings up this common misinterpretation
Yeah.
that Wittgenstein was a logicist in the Tractatus.
Uh-huh.
So, I guess, why did this interpretation even come about, and what are the arguments against it? Like, what should we as philosophers be thinking about here?
Right. Well, the logicist interpretation, I mean, it's understandable why people saw it that way.
Right.
There are several reasons. First of all, Wittgenstein himself states, straight out that mathematics is a method of logic.
Right.
Secondly, he observes that the, quote, the logic of the world, unquote, is shown in equations by mathematics, just as it's shown in tautologies by logic.
Okay.
Thirdly, he argues that we figure out the truth of both mathematical and logical propositions by just looking at the symbols.
Right.
No need to go outside of them. And finally, his view of numbers as, exponents of an operation variable, some people saw that as a reduction of arithmetic to operation theory,
Okay.
where operation was kind of interpreted as logical.
Right, right. Yeah, those are some pretty strong points of overlap with, like, traditional logicism.
They are.
So where do the arguments against this interpretation come in?
Right. Well, the key counter-arguments are these. So first of all, when Wittgenstein says that mathematics is a method of logic, he could just mean that both disciplines, they use formal operations,
Right.
Stemming from that shared underlying structure.
Right.
Or he could be referring to the fact that mathematical inferences, they rely on logical principles.
Right.
So when he talks about the logic of the world being shown in both, he might actually be saying that mathematics, in its application to, like, counting and measuring,
Yeah.
it kind of reflects contingent facts,
Yeah.
rather than being reducible to logic itself.
I see.
Now, critically, Wittgenstein never actually defines numbers logically in the specific rigorous way that, Frege or Russell did. And the similarity that he sees between tautologies and true mathematical equations, it's not one of, like, strict identity or reducibility.
Right.
And finally, scholars argue that there's really no evidence that Wittgenstein's notion of operation is actually logical in their very specific sense. It seems to be more of a formal syntactical operation.
Yeah.
As he later clarified, logical operations are performed with propositions, arithmetical ones with numbers.
Okay, that's helpful. That clarifies a really important distinction.
Yeah.
So even in the Tractatus, while there are these clear parallels between logic and mathematics in their formal nature,
Yeah.
he's not trying to collapse one into the other in that really strong logicist way.
Right.
Okay. Now, the encyclopedia also briefly mentions the practical application of mathematics as viewed in the Tractatus.
Yeah.
How does that fit in with this purely formal perspective?
That's a really interesting point. And it's actually a point of some tension and, ongoing discussion among scholars about the early Wittgenstein.
Yeah.
So he states that we use mathematical propositions only in inferences from non-mathematical to non-mathematical propositions.
Okay.
So in other words, we use them to reason about the world.
Right.
Now, he often emphasizes this idea of looking at the use of a word or a proposition to gain philosophical insights.
Yeah.
So while mathematics itself is seen as this purely formal syntactical system,
Yeah.
he does acknowledge its role in helping us reason about the empirical world.
Okay.
But the Tractatus doesn't really spell out how these non-genuine propositions, these equations,
Yeah.
how they actually help us make those inferences between genuine contingent propositions.
Right.
And this is a question that he's going to come back to and try to address more directly with this idea of extra mathematical application in his later work.
Oh, okay. So the Tractatus kind of lays this formalistic groundwork.
Yeah.
But it leaves us with a bit of a puzzle regarding the connection between this abstract system and how we use it to understand the world around us.
Right. Okay.
Okay, so this brings us to what's often called the Middle Wittgenstein,
Yeah.
roughly from 1929 to 1933,
Yeah.
which is characterized by what the encyclopedia calls finitistic constructivism and formalism.
Yeah.
So what were the big changes in his thinking about math during this time?
Well, this period, it's marked by a pretty significant shift, and it's heavily influenced by his engagement with the work of mathematicians like Brouwer, Weil, Hilbert, Skolem,
Mm-hmm.
but also these really insightful conversations that he had with Frank Ramsey and other members of the Vienna Circle.
Right, right.
So the core development here is towards a more explicitly articulated formalism.
Okay.
And he really emphasizes this idea that we make mathematics. It's not about discovering pre-existing mathematical truths.
Mm-hmm.
It's about actively inventing formal calculi.
Inventing rather than discovering.
Yeah.
That's a pretty radical reorientation for a philosopher who's used to thinking about, uncovering truths, right?
Absolutely.
It's a huge shift.
Yeah, it's a big one. He sees mathematics as this activity of creating these purely formal systems,
Yeah.
complete with, stipulated axioms and syntactical rules. And within these invented systems, mathematical truth and falsity,
Yeah.
those are then established by algorithmically deciding propositions according to those rules of the calculus.
Hmm.
So the focus here is very much on the syntactical nature of mathematics,
Right.
entirely devoid of any kind of inherent reference or semantics.
Yeah.
And this really puts him in direct opposition to, any kind of mathematical Platonism.
Right. Okay, so in this view, numbers aren't these abstract things floating out there in some realm of forms.
Right.
They're tied to the symbols that we're actually manipulating within these systems.
Precisely. For the middle Wittgenstein, numbers are the numerals. Arithmetic doesn't talk about numbers as these separate objects.
Yeah.
It operates directly with these symbolic representations.
Okay.
And he draws this really compelling analogy here, comparing arithmetic to a kind of geometry,
Oh, okay.
where the calculations we do on paper, those are like the arithmetic equivalent of geometric constructions.
I see.
The meaning of a mathematical proposition, it's completely internal to the system.
Yeah.
Defined by its syntactical relations to other parts of the calculus.
Right.
We are the creators of these mathematical truths.
Hmm.
They don't exist out there waiting for us to discover them.
Okay. And during this time, he goes so far as to say that, application outside of mathematics isn't actually required for a mathematical calculus to be valid.
That's right. So his view then was that we could actually develop a system of arithmetic completely on its own.
Yeah.
And its potential for application, that would kind of take care of itself.
Sure.
Wherever the structure of the calculus happened to align with aspects of the world, then we could apply it.
Right.
But the calculus itself stood on its own. It didn't need that immediate connection.
Okay. Now, the concept of decidability becomes super central in his philosophy of mathematics during this period, right?
Yeah, it does.
So how does this, focus on formalism connect to the idea of whether we can actually answer a mathematical question?
Well, drawing a lot on Brouwer and Hilbert, He makes a very strong connection between mathematical meaningfulness and the idea of algorithmic decidability.
Hmm.
He says an equation is basically like a rule of syntax.
Okay.
And this very nature is what explains why we can't have mathematical questions that are, in principle, unanswerable.
Right.
If the rules of the game don't provide a way to decide a proposition,
Yeah.
then that proposition doesn't have a clear place within the mathematical system.
Hmm.
This fits perfectly with that formalist picture of mathematics as like a rule-governed game that we play with symbols.
Right. And the encyclopedia points out that he takes an even stricter stance than, like, Hilbert and Brouwer on the law of the excluded middle in this context.
Yeah, that's right. So while they were also thinking about the scope of the law of the excluded middle, Wittgenstein, he basically maintains it by just restricting the domain of meaningful mathematical propositions
Hmm.
to those that are algorithmically decidable. If the law of the excluded middle, which is, for any proposition, either it or its negation must be true,
Right.
if that doesn't apply,
Yeah.
then for him, we're not really dealing with propositions in mathematics at all.
Okay, so for the middle of Wittgenstein, a meaningful mathematical proposition is one where we have a definite method to determine if it's true or false within the system.
Yeah.
Okay. Now let's get into the finitistic aspect of his thinking.
Okay.
What exactly does his finitism entail, and what does it mean for how we understand math?
Okay, so this is where we see a really big departure from his views in the Tractatus.
Yeah.
The middle Wittgenstein, he rejects the idea of quantifying over infinite mathematical domains. His argument is that we can't understand these as like infinite conjunctions or disjunctions.
Simply because, for him, there are no such things as completed infinite mathematical extensions.
Okay.
The only infinity that he allows is what he calls the infinite possibility of finite series.
Okay, so why this, like, pretty radical move towards finitism? What's behind this rejection of infinity in math?
So there are a few key reasons. First, his view of mathematics as a human invention. If we create mathematical objects through our constructions,
Yeah.
then they don't have an existence beyond those constructions.
Right.
Second, he believed that mathematical calculi consist only of finite extensions.
Okay.
So concrete symbols, finite sets, finite sequences, and intensions, which are like the rules of inference,
Right.
with things like irrational numbers actually being understood as rules themselves.
Okay.
So these finite components, for him, they make up the entirety of what we can legitimately call mathematics.
Okay, and what are the implications of this finitistic view? Like, how does this impact his philosophy of mathematics?
The ramifications are pretty huge.
It leads to a rejection of completed infinite mathematical extensions.
Okay.
A mathematical infinite can only exist, so to speak, in those rules that generate finite sequences.
I see.
Consequently, it means we can't have unbounded quantification in math, because a meaningful mathematical proposition needs to have a determinate sense.
Yeah.
And there can't be infinitely many propositions that make up that sense.
Right.
It also means that all genuine mathematical propositions are, in principle, algorithmically decidable.
Okay.
The notion of an undecidable mathematical proposition becomes a contradiction in terms. His finitism also results in this anti-foundationalist view of real numbers. So he sees irrationals as rules rather than infinite extensions, which then leads to a dismissal of a comprehensive theory of the mathematical continuum, or the existence of different infinite cardinalities.
He's really taking aim at this very deeply ingrained idea of infinity as a completed actual thing in math.
He is. He argues that we often make this fundamental error. We confuse mathematical intensions, which are the rules or laws,
Right.
with mathematical extensions, which are those potentially infinite lists generated by those rules.
Okay.
We tend to think that because a real number can endlessly produce decimal places,
Yeah.
it is an infinite totality.
Right.
But for Wittgenstein, an irrational number, it's not the extension of an infinite decimal. It's the rule that generates that extension.
Okay.
And a rule and a list, no matter how long, those are fundamentally different.
I see.
He famously said that the mistake in the set theoretical approach consists time and again in treating laws and enumerations, lists, as essentially the same kind of thing. And this confusion, he thought, was the root of our mistaken belief in the actual infinite in mathematics.
Okay, and he even has a critique of how we use the word infinite in a mathematical context.
He does, yeah. He says that infinite is not a quantity word like, 5 or 17. They don't work the same way in our language.
Right.
Saying infinite class and finite class
Yeah.
actually uses class in totally different senses.
Yeah.
An infinite class, for him, it's basically a recursive rule, a method of generating elements indefinitely, whereas a finite class is just a list,
Right.
a determined list of elements. So we kind of mistakenly apply class to both, and it leads to this illusion that an infinite class is just like a really, really, really long finite class.
Right, right.
So when we say there are infinitely many even numbers, we don't mean there's an infinite number of them in the same way there might be, like, 27 people in a room.
Yeah.
It's about the infinite possibility of finite series of even numbers that can be generated according to the rule.
It's a radically different way of thinking about infinity in math.
Yeah.
And this obviously has big implications for how he sees mathematical quantification.
Absolutely. If a set is fundamentally a finite extension generated by a rule,
Yeah.
then we can't meaningfully quantify over an infinite mathematical domain because, for him, no such completed domain exists.
Okay.
This means we can't have infinite conjunctions or disjunctions
Right.
in a meaningful mathematical proposition.
I see.
He even thought the idea of God, an omniscient being knowing all the places of pi, was senseless in a mathematical context.
Wow.
For him, a statement about all numbers, it's not represented by a single proposition. It's represented by the method of induction, which shows us how to proceed for any particular number.
Right.
Similarly, existential quantification over infinite domains is also rejected. What would such an infinite disjunction even mean in a constructive framework?
Okay, so for him, even an expression that seems to quantify over an infinite domain,
Yeah.
even if we have a proof for any specific instance within that domain,
Yeah.
it's not a real proposition in the usual mathematical sense.
Not in the same way, no.
Okay.
He takes the stance that all expressions that quantify over infinite domains, whether they're currently unproven conjectures like Goldbach's conjecture,
Yeah.
or seemingly well-established general theorems like, Euclid proof of infinitely many primes,
Yeah.
they don't have the status of genuine mathematical propositions.
Because the law of the excluded middle wouldn't apply in a meaningful way to those statements about infinite domains.
Exactly. For Wittgenstein, where that law doesn't have a clear application,
Yeah.
we're not dealing with propositions of mathematics in the proper sense.
Right.
He goes on to say that there are these 4 categories for how we can string together mathematical symbols.
Okay.
So first, those that have been proven within a calculus. Second, those that have been refuted.
Right.
Third, those for which we have a known and effective decision procedure.
Okay.
And finally, those that aren't propositions at all,
Yeah.
because they lack that kind of procedure. And this third category,
Mm.
the ones where we know we have a method to decide their truth or falsity,
Right.
that's absolutely key to his understanding of mathematical meaning during this period.
Okay, so that leads to a pretty unconventional view of long-standing mathematical conjectures like Goldbach's conjecture and Fermat's last theorem.
Right.
If they're not decidable by a known method, what are they? What status do they even have?
Well, he argued that these conjectures, which have kept mathematicians busy for centuries,
Yeah.
they don't have a determinate sense until a proof is actually discovered. The very act of finding a proof is, for him, like creating a new calculus
Okay.
or extending an existing one. And this then gives the proposition a meaning that it didn't have before.
Right.
So he famously said that Fermat's last theorem makes no sense until we can search for a solution to the equation in cardinal numbers in a systematic way.
I see.
And search here, it very specifically means a systematic procedure, not just kind of randomly trying things out.
Right, right. And how does mathematical induction, which is such a powerful tool, how does that fit into this framework that really emphasizes finitism and decidability?
Yeah, that's a great question. Given that he rejects quantification over infinite domains,
Yeah.
Wittgenstein reinterprets what induction actually does.
Okay.
He says that it doesn't prove a universal proposition in the traditional sense. A statement that holds for every number in a completed infinite set.
Right.
Instead, what induction does is it acts as a kind of proxy statement. That stands in for any particular number that we might pick.
Okay.
So the inductive process, it reveals this infinite possibility.
Right.
It shows us how to construct a proof for any specific number, even if we don't actually do it.
Right.
It's about recognizing a general method of proof, rather than proving a truth about an actual infinite collection.
And he connects this back to his rejection of undecidable propositions as well.
He does. He believed that a proof actually changes the grammatical status of your proposition.
Okay.
If we can't decide whether a mathematical statement is true or false,
Mhm.
then it doesn't really function as a proposition within a calculus where we have, methods for deciding things.
Right, right.
He contrasts this with intuitionists like Brouwer, who allowed for propositions whose truth value might be inherently unknown. But for Wittgenstein, conjectures that we don't have a decision procedure for.
Yeah.
They're simply not mathematical propositions at all. A mathematical proposition for him during this time is defined by the fact that it's either already decided or it's decidable through a known method within a specific system.
So from Wittgenstein's perspective, in this middle period, these big, long-standing conjectures,
Uh-huh.
they're not really meaningful questions with unknown answers.
Mm-mm.
They're more like potential starting points for us to expand math or create new systems.
Exactly.
Hmm.
He sees attempts to prove or disprove them as, quote, unsystematic attempts at constructing a calculus, unquote.
Right.
If we do find a proof, we're not uncovering some hidden truth.
Yeah.
We're establishing a new calculus where that proposition now has a definite sense and a definite proof status.
Okay, that's really interesting. Now, he also spends a lot of time thinking about irrational numbers in this period.
Yeah.
What's his take on those from this finitistic and constructivist point of view?
So he sees that picture of an irrational number as this infinite completed decimal expansion, as a big reason why people believe in the actual infinite in math.
Hmm.
He argues that the confusion comes from not really understanding what an irrational number is.
Okay.
For Wittgenstein, an irrational number, it's not that infinite decimal expansion.
Yeah.
It's a rule or a law that generates a sequence of rational numbers that get closer and closer to the irrational.
Okay, so numbers like the square root of 2 or pi,
Yeah.
they're not these infinitely detailed decimals stretching out forever. They're finite rules that let us calculate those decimals to whatever precision we need.
Exactly.
Hmm.
The rule for calculating the decimal places of root 2, that is the numeral for him.
Oh, I see.
We consider it a number because we can work with those rules.
Yeah.
We can compare them,
Right.
use them in calculations,
Yeah.
just like we manipulate rational numbers.
And this view of irrational numbers as rules rather than infinite extensions, this connects to his anti-foundationalist stance on real numbers and the idea of a continuous mathematical line.
Absolutely. So since in his system there are no completed infinite extensions,
Yeah.
irrational numbers, being rules, are also not infinite extensions.
Right.
And since no finite set of rules can generate all the things that mathematicians call real numbers, he concludes that there's no such thing as a set of all real numbers,
Okay.
and no mathematical continuum in the way it's usually understood.